powerful eruptions, breathtaking views across the solar poles, and a strange solar hedgehog are among the incredible haul of spectacular images, movies, and data returned by Solar Orbiter from its first close approach to the Sun. Although the analysis of the new dataset has only just begun, it is already clear that the ESA-led mission is providing the most extraordinary insights into the Sun's magnetic behavior and the way this shapes space weather. So, let's talk about it. Welcome to Space World. In today's video, we are going to talk about incredible new views of the Sun, which have never been seen before. So if you want to know more about it, then stay with us until the end of the video. Solar Orbiter's closest approach to the Sun, known as perihelion, took place on March 26. The spacecraft was inside the orbit of Mercury at about 1/3 the distance from the Sun to the Earth, and its heat shield was reaching around 500 degrees Celsius. But it dissipated that heat with its innovative technology to keep the spacecraft safe and functioning. Solar Orbiter carries 10 science instruments. 9 are led by ESA member states, and 1 by NASA, all working together in close collaboration to provide unprecedented insight into how our local star works. Some are remote sensing instruments that look at the Sun, while others are in situ instruments that monitor the conditions around the spacecraft, enabling scientists to join the dots from what they see happening at the Sun to what Solar Orbiter feels at its location in the solar wind millions of kilometers away. When it comes to perihelion, clearly the closer the spacecraft gets to the Sun, the finer the details the remote sensing instruments can see. The images are really breathtaking, says David Bergmans, Royal Observatory of Belgium and the principal investigator of the Extreme Ultraviolet Imager instrument, which takes high-resolution images of the lower layers of the Sun's atmosphere, which is known as the solar corona. This region is where most of the solar activity that drives space weather takes place. The task now for the EUI team is to understand what they are seeing. This is no easy task because Solar Orbiter is revealing so much activity on the Sun at the small scale. Even if Solar Orbiter stopped taking data tomorrow, I would be busy for years trying to figure all this stuff out, says David Bergmans. One particularly eye-catching feature was seen during this perihelion. For now, it has been nicknamed the hedgehog. It stretches 25,000 kilometers across the Sun and has a multitude of spikes of hot and colder gas that reach out in all directions. However, Solar Orbiter's main science goal is to explore the connection between the Sun and the heliosphere. The heliosphere is the large bubble of space that extends beyond the planets of our solar system. It is filled with electrically charged particles, most of which have been expelled by the Sun to form the solar wind. It is the movement of these particles and the associated solar magnetic fields that create space weather. To chart the Sun's effects on the heliosphere, the result from the in situ instruments, which record the particles and magnetic fields that sweep across the spacecraft, must be traced back to events on or near the visible surface of the Sun, which are recorded by the remote sensing instruments. This is not an easy task as the magnetic environment around the Sun is highly complex, but the closer the spacecraft can get to the Sun, the less complicated it is to trace particle events back to the Sun along the highways of magnetic field lines. The first perihelion was a key test of this, and the results so far look very promising. On March 21, a few days before perihelion, a cloud of energetic particles swept across the spacecraft. It was detected by the energetic particle detector, and the most energetic of them arrived first, followed by those of lower and lower energies. This suggests that the particles are not produced close to the spacecraft, says Javier Rodriguez Pacheco, University of Alcalá, Spain, and EPD's PI. Instead, they were produced in the solar atmosphere, nearer the Sun's surface. While crossing space, the faster particles pulled ahead of the slower ones, like runners in a sprint. On the same day, the radio and plasma waves experiment saw them coming. Picking up the strong characteristic sweep of radio frequencies produced when accelerated particles, mostly electrons, spiral outwards along the Sun's magnetic field lines. RPW then detected oscillations known as Langmuir waves. Of the remote sensing instruments, both EUI and the X-ray spectrometer telescope, STIX, saw events on the Sun that could have been responsible for the release of the particles. While the particles that stream outwards into space are the ones that EPD and RPW detected, it is important to remember that other particles could travel downward from the event, striking the lower levels of the Sun's atmosphere. This is where STIX comes in. While EUI sees the ultraviolet light released from the site of the flare in the atmosphere of the Sun, STIX sees the X-rays that are produced when the electrons accelerated by the flare interact with atomic nuclei in the lower levels of the Sun's atmosphere. So, exactly how these observations are all linked is now a matter for the teams to investigate. There is some indication from the composition of the particles detected by EPD that they were likely accelerated by a coronal shock in a more gradual event rather than impulsively from a flare. It could be that you have multiple acceleration sites, says Samuel Krucker, FHNW, Switzerland, and PI for STIX. Adding another twist to this situation is that the magnetometer instrument, MAG, did not register anything substantial at the time. However, this is not unusual. The initial eruption of particles known as a coronal mass ejection, CME, carries a strong magnetic field that MAG can easily register. But energetic particles from the event travel much faster than the CME and can rapidly fill large volumes of space and therefore be detected by Solar Orbiter. But if the CME misses the spacecraft, then MAG will not see a signature, says Tim Horbury, Imperial College, UK, and MAG PI. When it comes to the magnetic field, it all begins at the Sun's visible surface, known as the photosphere. This is where the internally generated magnetic field bursts into space. To know what this looks like, Solar Orbiter carries the Polarimetric and Helioseismic Imager, PHI, instrument. This can see the north and south magnetic polarity on the photosphere, as well as the rippling of the Sun's surface due to seismic waves traveling through its interior. Another instrument, the Spectral Imaging of the Coronal Environment, SPICE, records the composition of the corona. These abundance maps can be compared to the contents of the solar wind seen by the Solar Wind Analyzer, SWA, instrument. Now the question is that, what are scientists going to do with all the data gathered by each instrument? By combining data from all instruments, the science team will be able to tell the story of solar activity from the surface of the Sun out to the solar orbiter and beyond. And that knowledge is exactly what will pave the way for a future system designed to forecast the space weather conditions at Earth in real time. In the lead-up to perihelion, Solar Orbiter even got a taste of how such a system might operate. And this is it for today, guys. What are your thoughts on today's video? Share your views with us in the comments below. And don't forget to give this video a thumbs up, subscribe to the channel, and ring the bell icon for more amazing videos about space. And thank you for watching.